Hi everyone, I'm going to show the Sherlock V1 contracts, the solidity itself. If you haven't watched the Sherlock conceptual video, you should watch it first. It explains Sherlock a little bit more from the conceptual side, and this is more in depth about the solidity itself. So it's a hard hat repository, just like a regular setup with the contracts folder containing all the contracts and the test containing all the tests. As you can see, we have 100% test coverage, so that's that's decent. The contracts are organized as follows. The facets contain like all the logic, and the facets import storage. It's like an external library. So we are using the diamond standard. If you want to know what it is, you should look at the conceptual video. So the storage is like just like a library that returns a pointer to the struct. So then the storage can be used for every single storage layout. As you can see, like the functions are not commented. These are commented in the interface. So if you want to know the comment about this, you just go to the interface and you can see the docstring. There's also documentation generated, which is available at docs.sherlock.xyz. So be sure to check that out. So I will first go over the life cycle of a protocol. Protocols are added using the protocol add function, which can only be called by governance. It uses like a byte32 identifier of the protocol. Adds like a protocol agent, which is like an address that belongs like to the protocol, and the manager, but this is currently not used, and an array of tokens that a protocol is able to pay the premium in. So this calls update. So it adds like the protocol to the storage, and protocol deposit add loops over all the tokens, and adds like based on the token, it like calculates like the storage pointer and retrieves the pool storage for that particular token, and then for that particular token, it initializes the protocol as like a protocol, and it pushes it to the array. So now the protocol is registered as a protocol in this particular token. So this is like on protocol level, and on the protocol add function, it's also like on the scope storage. It's also added as a protocol. So basically, a single protocol could have like 0 to unlimited tokens. They can be added to, and you can check like if a protocol is added globally by this storage variable. So this is basically the way of adding a protocol. A protocol can also pay premium, of course, and this is done in a different facet, or in a different facet. That's also like every facet shares the same storage, so it doesn't really matter. So what's happening? Set protocol premium can be called by the governance again, and there are like multiple variation of this function. So you can go to the interface. It's like token price. We'll go over that later. Set protocol premium, and there's like 5 or 6 variations based on and the needs at the time. A different function can be called. So the basic one is set protocol premium, which is like the protocol, the token, and the premium. And yeah, so what basically happens, the old variables, USD per block and USD pool, these are two variables that are used to calculate the amount of sherx that needs to be distributed. And these are read from storage this way. And go to the getData function. So it's just like reading from storage and returning them. And then it calls like an internal function set protocol premium, which forwards the old or like storage variables and returns like the updated variables, and it sets the data. And so it writes to storage again these updated variables. And so what do we mean like with a token price? Here is the same function, only there's one variable added. It's like the USD value. So we keep track of like an internal USD value of the token to make sure like the stakers are rewarded the right amount of sherx, and to make sure the protocols are not overpaying their premium. And yeah, so we use like an internal USD value that is somewhat accurate, but not always accurate, but that's good enough for like this use case. So what happens here is like the same thing, reads from storage, updates like the internal variables, and it writes to storage again. And why this pattern is used, because there's also like functions that contain loops and loop over all the protocols, and then just only like writes to a storage once. So for example, here it updates variables, and you can have like a looping 10 times and writes to storage only once, which is like a gas optimization. So what happens exactly we'll go for this one. What happens in set premium and token price, like the internal, like a private function. There are some validations, and the new token price is set. The new protocol premium is set. It basically, writes to storage how much the protocol will pay in premium. The new data is updated, and this is returned. So update data. So it's like there are a certain amount of tokens paid as premium per block. For example, if we have two protocols paying 100 DAI per block, like the total is 200 DAI per block, and based on the stored USD value of DAI, you can say if that's $1, there's like $200 per block. Like maybe DAI is not as good as an example, but for example, ETH or wrapped ETH can change in price. And if the price of wrapped ETH changes, like the amount of USD per block that's distributed, that's received, is also changing. And the total amount, which is like the USD pool, so if they pay $200 for 10 blocks, there's already 2K in the pool. And then if that consists of ETH and the ETH price doubles, that 2K becomes 4K. And this function is to make sure like those variables are updated well. And it does it like in memory and returns the in-memory variables, which are later written to storage. So set data is like always the last function for every function that's defined there. So this accrues like the sherx. So it's basically like minting all the sherx that is like up to this block. based on the current supply of sherx. This read from like the sherx storage. If this is basically the starting point. So if the new distribution is like more than 0 USD per block, so there's like premium coming in, and there's no total supply yet, then we distribute 1 sherx per block. If there is already like a USD pool, if there was already like distribution before, we calculate a new amount of sherx per block based on these 3 variables. And well, if there is like no USD per block, if it's like 0 premiums coming in, we don't distribute anything. And then we keep like internal supply for like gas reasons. I can explain it later. And we write like the total USD per block and less settled to the current block. So on every like premium update or internal USD value update, this function needs to be called and the sherx needs to be accrued. So like all this logic is like pretty gas optimized, which could make it a little harder to read. But basically every external function does less or more the same thing, and it just calls these private functions. So this like the purpose of this function manager is to make sure the protocol accrues the right amount of debt per block, and the right amount of sherx is minted per block, and the sherx is distributed to stakers or to the Watsons, and I will go over that later. So let's go one step back to the governance. So protocol is added with like an array of tokens, for example, DAI, RepBTC, and this allows the protocol to pay a premium in those tokens, and allows like the account calling these functions, the governance, to set a premium for the protocol in these particular tokens, so DAI and RepBTC. And then the protocol, if a variable is set, for example, token RepBTC 100 BTC per block, then the debt of the protocol starts accruing per block. And if the protocol wants to pay off that debt, this is happening in the pool base with the deposit protocol balance. So anyone can call this function with that protocol identifier, the amount and the token, for example, 1000 RepBTC, and then the protocol balance is stored like internally. So then the protocol has like a runway for their to pay off their premium. So to pay off the debt, that function is called pay off debt. This is the internal one. One sec. Okay, pay off debt all, pool base. Oh yeah. So what this does is basically pay off debt all for the token, which goes to the library to pay off the debt. And the library is defined here. So what it does, so if multiple protocols are paying like in the same token, then it keeps like track of this total sum that's get paid per block, and it can also only be paid off like at the same time. So what happens, for example, protocol 1 and protocol 2 are both paying in DAI, like 100 DAI per block. Then the total premium less paid, like it's the same for both protocols, so they both pay at the same time. So what happens, it loops over both protocols, like it calls payoff debt for each protocol, and this function will revert in case there is not enough balance. And this is also by design, and what needs to be done by the governance is to make sure this never happens, but it's tricky, could be tricky. Yeah, so it calculates the currently accrued debt based on the, like the blocks, the amount of blocks. It subtracts that from the protocol, from the active balance, and it returns the debt. So it sums like all the debt of all the protocols paying premium with this token, and this is added as like the sherx underlying. So move funds to the sherx ETF, and it sets like the premium less paid to the current block. So this is how protocols can pay deposit balance and pay their premium. So in case like a protocol needs to be removed, which can happen of course. So for example, protocol pays in red BTC and DAI, then the protocol needs to be cleaned from both of these pools. So this, for example, could be protocol X, and like the index is from the array is like defined off chain, and this could be DAI. So based on the token, it gets like the pool storage, and this is like an internal function to get like the right storage pointer. Like based on if the protocol has like an active premium or like has more debt accrued than they have balance, like the protocol can be removed and like popped from the array, which is like actually removing them. And subtracts like if there is still an active premium, it subtracts it from like the total premium per block. And in case like there is a leftover balance, it transfers it to the receiver, which could be the case. So this is just like to clean the protocol from the pool storage and to make sure there's no active balance for the protocol in that token, and to make sure like the array is getting shortened. And to completely remove the protocol, protocol remove is called, and this checks if there is no if it's not currently in the pool storage, in the token storage, and just like deletes everything from the protocol. So this is basically everything about protocol. So we went over like adding a protocol, paying the premium, and how the premium works, and then like removing the protocol from the pools, the token pools, and the token they pay the premium with, and then like this finally completely removing the protocol from like the global storage. So I've showed how protocols are added and how it's calculated how much sherx is minted. And the minted sherx is distributed to stakers in certain pools and to Watsons. And I will now show how stakers interact with this solution. So we basically like pool open, which is like stake, and calling like the internal stake function, which is used like in production once everything is ready. We have pool def only, which requires like calls the same internal stake function, but requires like the sender to be the owner. So like in production we can use it to get some things right. So what happens in like first it checks if like the token that's staked in like is in the array. So then it basically means it's also kept as like a boolean. So if it's like stakes, so if you're eligible to stake in this token, and so I need to go over that logic first, how that works, and that is done in the governance contract. So for every token that the governance wants the stakers to stake in, token init is called, and this function can be called multiple times. So like the token is ERC20, the address, the gov pool. So this is like an address that governs the strategy and like other specific things for that particular token. This is like a log. It's like an interface, and if this is not 0, then stakers are able to stake in this token, and this address represents like the log token that is used like to represent a staked token. And a bool protocol premium, so if this is true, then the protocol is also able to pay a premium, their premium in this token. That needs to be added first, as I showed before. But yeah, how it works. So here it like checks if the log is not 0, and the log is like an interface, and it checks if like the interface, like the interface is implemented well, and if like the current variables are expected. And then it writes to like the storage, calculated to the pointer of the token. It writes, okay, a log token is there, and then checks if if it is like stakeable. Then it writes to stakes is true, and it pushes it to the array. So this is an array in the gov storage, and that array is like an array of all the tokens stakers can stake in. And if a protocol premium, it pushes like it to the sherx array, and the sherx array is like all the tokens the protocol can pay the premium with, and it also sets a boolean premium is true to like check in a guess optimized way if this token can be used to pay premium. So this is how tokens are initialized. And so if a log token is provided, which means it can be used to stake, then stakes is set to true, and so it allows people to call this function. So that's pretty straightforward. The token is transferred to this contract, and we use a library for the staking function. So if it's the first person staking, there is like one log token minted. So if you stake 100 DAI, you get one log DAI, and so the exchange rate is like 100. And if you stake 1 DAI, the exchange rate is 1. So the first depositor sets the exchange rate, and if there is already like a certain amount, like it's calculated based on the exchange rate. It's added to the balance, and log token is minted to the receiver. So now the staker is like a stake in the solution. Well, stakers can also activate the cooldown to get the money out. And so it transfers the lock token to the solution, and we can create a cooldown fee. And there's an entry added to the unstake storage, and based on the storage, people are able to cancel the cooldown. And this is like if the window of opportunity to unstake is expired, you can call this function to get like your tokens back. So it transfers it back to the original user. And if you're in the window of opportunity, you can unstake, and the actual like underlying tokens are transferred back to the user, to the receiver. So this is how the stake, basically all the functions the staker needs to call. And you might ask, how is the staker rewarded for this? Well, this is in sherx, of course. And sherx, let me go to the lock token. So lock token is like before token transfer. And we have like foreign lock and native lock. And native lock is used for sherx. So you can also like stake sherx, and we needed a different implementation for that. And for DAI, RapBTC, and other like native, like foreign tokens, we use the foreign lock. So before token transfer is like the before token transfer function is called in the solution. This is defined here. Before token transfer, and this calls the function do yield, which is basically like distributing the right amount of sherx to the to the person transferring the token. So this like code is reused from like liquidity mining contracts. So with liquidity mining, most of the times you stake like token X, for example, like a Uniswap like liquidity, like a token, and you get like other tokens as rewards. And this is like the logic we also use in here. So you have like DAI and you get rewarded sherx. So if the from is not 0, so it's not minted, then this is from the liquidity mining contracts. Then it's calculated like your withdrawable amount, and this sherx is already minted, but it subtracts it from the unallocated sherx because now it's allocated to the from user. And based like this function is hit if you send it as like a person, it stakes like your sherx on behalf of the user. So if you like receive sherx for staking DAI, you start accruing like sherx per block. And once you transfer your lock token, or you call the harvest function, which is defined up here, which basically calls the same function as like the before transfer. And if you call that as a person, like you accrued like sherx over time, and if you start to harvest it, then it's like staked. So you always received like lock sherx, and you are able to activate the cooldown and get it out. Mm, so if from is address this means if like the solution itself is transferring the lock token, which is the case in case like people are activating the cooldown and the lock token is in the contract, and then the solution like burns it or sends it back, then the from is this, and then it's added to the first money out like pool basically, and that means that's like a protocol controlled value that is used in case of like exploits. Then this is like the tokens that are used first for that exploit. Yeah, and for the rest, like this is all like from the liquidity mining contracts. So let's see like how does accrue sherx actually work. Because as you can see here, like the withdrawable amount based on like the raw amount, and the raw amount is based like on the user amount and the total amount and the weight. And yeah, let's see how this function actually works. This is not the right one. Oh wait, this is the right one. So sherx is like accrued to certain pools. As you can see here, it loops over all the pools that people are able to stake in, and it does like the internal accrue sherx for like the every token, and this is like the total amount of sherx that's distributed. So what happens, like here it calculates like how much sherx is rewarded to this pool. So based on like the amount of blocks like ago, multiplied by the total sherx per block, multiplied by the certain weight of this particular like token, divided by UN16. So UN16 like minus 1 is like the 100% of the sherx is distributed. And UN16 like 50%, then it's just like 50% of the total sherx is distributed to this pool. If like the sherx is 0, return 0, and otherwise it adds it to the weight. So that function of that variable is used. Oh wait. That function is used here to calculate like the ineligible amount, which is in return used for like how much the protocol of it, how much the user is can claim, and also adds to the unallocated. And yeah, so for sherx we use like a stake balance instead of this one for gas reasons. Yeah, so the weights are also interesting, or I will show you how the function works. So initial weight. So the initial weight is like setting 100% of the sherx is distributed to the Watsons. So what it does, it requires the Watsons to be set, loops over all the tokens the staker can stake in. It requires like the weight to be 0, otherwise this function like was called somewhere before. And then it's just like, okay, instead of like everything being 0%, it's now Watson's 100%. And that weights can be called like over time to change those weights. So for example, if this is like, if there's like a die pool and I want to give 20% of the sherx rewards to that die pool, this can be die, this can be like 20%, which is like a fifth of this variable, and this is like 80% of the variable, so 80% is still distributed to the Watsons, and this logic is like executing on that. So in the end, it's like so like this is like the die token, and die is like the right weight is like initialized. So this is like how sherx is distributed, and how it's like the weights can be altered to give different rewards to different pools, and how stakers can like take a part of that pool by the lock token, and how the lock token is used to harvest the sherx basically. So sherx can be redeemed for the underlying tokens, and this is can be done in a sherx function. So redeem. So if a certain amount, the receiver. So what happens is your sherx that you like send is burned, and based on like the tokens and amounts, the like the underlying amounts are transferred to the receiver, and everything is settled, and like some internal accounting is done to make sure like the USD pool are still up to date, because tokens are transferred from the underlying, so that like shrinks the USD pool that's used to calculate like the amount of sherx to distribute. And that's basically how sherx works. So like one good thing to know is like the storage of sherx is also in the like the address of sherx is like the same address as the solution. So the solution is like ERC20 compatible, and it also has ERC20 storage. Oh, this is the library. ERC20 storage is like the name, the symbol, the total supply, the balances, and the allowance. And we have an ERC20 facet, which can expose like the default functions like transfer from. So it's like ERC20 compatible solution, and the ERC20 it exposes is like the sherx. So for this last part, I'm going to talk about the payouts. So the payouts is a pretty long function, and takes a couple parameters. So the first parameter is the payout address. So all the funds that are like defined here are transferred to this address. So an array of tokens which represent like the staking pools are can be passed here, and from the token the amount that needs to be transferred from the first money out pool, from the staking balance, and from the unallocated sherx. So unallocated sherx is like stakers are like accruing sherx over time, and they can harvest it every block. But if they didn't harvest it from like the block until this function is called, that is still unallocated, and that can be used in case of a payout. And the sherx is not transferred itself. All the underlying tokens are transferred. And one of those underlying tokens can be excluded using this parameter. So basically, here it loops over all the tokens, and just like subtracts the right values from the the storage here in the bottom. And if it's like unallocated sherx, it subtracts the right values from the right variables used to keep track of which staker is eligible for how much sherx. So all this sherx is like summed up in this variable, and it's added to the total, which is like the basics of the sherx. So in the end, the sherx is passed on to doSherx. It's a private function that's defined here. As you can see, it looks a lot like the redeem function, which is used like to redeem the underlying of the sherx. But the difference is it returns the sherUSD, which is the USD that is excluded from like the total amount of USD the sherx is worth, because this token is not transferred, and this is like the amount of USD it represents. So it doesn't subtract that from the burn amount. So it doesn't burn that USD value of those tokens that are excluded. And so the rest of the tokens are burned. They're represented USD value basically. So this is done because it's sorry, technical problem there. It's done because the sherx underlying dollar value doesn't need to like be different in the next like block. Otherwise, like people who are exposed to that token will get fucked. Strategy. So this is basically how the payout works, and yeah. I'll now talk about the strategy. So for every token pool, there can be a strategy. This is the strategy facet, where like a strategy can be updated, basically added, and removed, and like protocol gov pool, it's like the governance of this specific token pool, can deposit funds into a strategy and withdraw it. So in case like 100% of all the tokens are all in a strategy, and someone tries to withdraw their funds, the funds are of the transaction is reverted, because the liquidity is not in the solution itself. So it's a job of the gov pool of this like person that can call this function to make sure there's always enough liquidity in the solution for the current withdrawals. And of course there's a cooldown period, so you can see the withdrawals coming, and it's a bit tricky, but it's the job of this governance address. So there is one actual strategy integrated. It's the Aave v2 strategy. Basically, like a DAI, wrapped ETH, whatever, is deposited into Aave, and like the balance is returned, and the balance is used in lib pool, for example, balance off. So to get the actual stake balance, it's calling the strategy, and that's used to return the active stake balance. Yeah, so that's basically the strategy. I have one more thing to show you. It's like the baseData, the thing that you see. Oh, it's not here, apparently. Oh, it's in the pool. So basically what this function does is like it takes the last parameter from the transaction, and it always ends with a token, so it's always the token, and it returns that like a pointer to that or like basically the pool storage with the pointer being like the token address.